Hi guys, my name is IBM and I welcome you to my YouTube channel, Learning Physics with IBM. Today I gathered the courage to solve past papers and I'm solving paper 5.2, that is for A-level physics 9702. So without wasting time, I would like to take you to the question paper. So this is the question paper, the candidate's name is IBM. Okay, so for those who don't know, I'm based in Asia currently. And this is paper 5, planning, analysis and evaluation, and it's supposed to be this is 9702 paper 5.2. This is May June 2023. The paper is supposed to be 1 hour and 15 minutes. So we are used to the instructions, and I would like to just take you straight away to the question paper. The best way to learn this is to print the question paper or have the hard copy of the question paper and maybe try to follow the video to get a picture of how to answer paper 5. My voice is not very good, but I will try. So two coils P and Q are placed close to each other as shown in the diagram. A resistor of resistance R is connected in series with the coil P. So of course, to measure the resistance R, you have two options. Either you use an ohm meter directly to measure R, or you must include an ammeter. You must include an ammeter and you put a voltmeter across. So to put the voltmeter across to be able to determine R from R equals to V over I. That is another option. Then a changing magnetic flux of frequency F in coil P causes an electromagnetic EMF E to be induced across the terminals of coil Q. So in P, there's a changing magnetic flux of frequency F. So how will I measure that magnetic flux? I need something to measure the frequency. Either I could use a signal generator or I could use a calibrated CRO. So that means I could put a calibrated CRO somewhere here. You could put a calibrated CRO, whatever way you put it. My students normally do this for the CRO. You could put a CRO here, or you could replace it with a signal generator. So this is a CRO calibrated, or you could replace the CRO with a signal generator. Just draw something and call it a signal generator. Then you just add the terminals to your circuit. Of course, this is connected to the power supply. So this one will be able to tell us the frequency, but how do I get the frequency from the CRO? From the CRO, frequency is equal to 1 over period, which will be 1 over the distance or the length represented by one cycle times the time-based setting, as we do this in paper 2 or in waves. Then on the other side, we have the induced EMF, E. So you may need a CRO this side to be able to tell, to measure the amplitude of the induced EMF. You could use a CRO. So you could add a CRO here. Because you want induced EMF, you could use an AC voltmeter instead of a CRO to determine the value of E. You could use a voltmeter which measures alternating current. So you would be looking for the peak voltage or the peak induced EMF. So you could use an AC voltmeter instead of a CRO. But if I use a CRO and I want the induced EMF, of course I want V. The induced EMF is amplitude. So I'll get the amplitude from the length or the length representing the peak of the cycle times the Y setting or the Y gain. That will give me the amplitude, which will be the induced EMF here. But for the AC voltmeter, you don't need to show any working for finding E. You just read. Here you just read the EMF from the AC voltmeter, just read the peak. Okay, then of course these coils, first of all, they should be a large number to produce a large EMF. There should be a large number of turns, large number of turns, and this should be, I think the number of turns should be constant. Secondly, to produce a large induced EMF, you may need to put an ion core into this coil. So you may need to put an ion core to concentrate the magnetic flux. And of course, because you have to keep the distance between the coils constant, the best thing would be to fix the coils onto the bench. So let me say I'm using a ruler. I've passed a ruler through the coils, and assuming this is the bench, so I'll use a G clamp to fix the coils onto the bench. So the coils must be fixed onto the bench or into the table if you want to keep the distance between the two coils constant. And it should be kept constant because if the coils move further apart, then that means the induced EMF reduces. Okay, so that is a skeleton of what we need. Now, it is suggested that E is related to R. So one of these must be independent and one of these must be dependent. So we are basically going to be changing R. So R is going to be the independent variable. And when we change R, definitely keeping the same, when we change R, keeping V constant, if we change R, then it means the induced EMF is going to change. So the E is going to be the dependent variable. So we shall keep V constant. So every time I'll be adjusting the CRO so that I get a certain frequency for which V is the same as before. So I'll ensure that V is constant. I will ensure that the distance between the coils is constant. I will ensure that the number of turns is constant, but I will ensure that I use a large number of turns so that I have a large value of E. I'll put an ion core so that the induced EMF is large enough. Okay, so where V is the potential difference across the coil, P and K and M are constants. Plan a laboratory experiment to test the relationship between E and R. Draw a diagram. We shall draw a diagram. Explain how the results could be used to determine K and M. So we have to modify this equation. So we have that E, I will say E into R plus K should be equal to 2 pi F M times V. So I want to make something related to E the subject. So because E is the dependent variable, and when we are plotting a graph, remember when we are plotting a graph, we always put a dependent variable on the y-axis and independent variable on the x-axis. So I want something related to E to be the dependent variable and something related to R to be the independent variable. So straight away I'll take E the other side, so it will be 2 pi F M V divided by E should be equal to 2 pi m 2 pi f mv divided by E should be equal to, on one side I'm running with R plus K. So again I will remove 2 pi f mv. So when I remove 2 pi f mv, divide both sides, I'll remain with 1 over E is equal to R divided by 2 pi f mv plus K divided by 2 pi f mv. So I've made 1 over r the subject, and that is making good sense to me. So I will plot a graph of 1 over r against r. So I'll plot a graph of 1 over e versus r. That is the graph I'll plot. And of course, this is going to be a straight line. If I compare with y equals to mx plus c, this is going to be a straight line. It is going to be a straight line. If I compare mx, because on the x-axis I have r, so the gradient is going to be 1 over 2 pi f mv, and that is the gradient, and the y-intercept. So this straight line will not go through the origin because it has a y-intercept. C is going to be k divided by 2 pi f mv. Okay, then Note that this is involving electricity, so you must suggest a safety precaution, how you will stay safe from being electrocuted by electricity or by current. So that is, I think that is a skeleton of what really I will be talking about. So it means if the gradient is known, then and I want to find k, so it means k will be equal to pi f m v times the y-intercept times the y-intercept. And then how to determine m? So it means m is going to be equal to, because gradient is equal to 1 over 2 pi f mv. So m is going to be equal to 1 divided by 2 pi fv times the gradient. So that is now the skeleton of my experiment. Now I can write it in words. So this should take you around 10 minutes. If you have the skeleton, then writing becomes very, very easy. So let's start. So in this experiment, in this experiment, so we have agreed that R is the independent variable, and E is the dependent variable. E is the dependent variable, so I will keep V constant. And I've showed you how you'll keep V constant. You'll be adjusting the CRO by adjusting the CRO. And I also said I will also keep the number of turns on both coils constant, because the number of turns affects the induced EMF, so it should be constant. Keep I will keep the number of turns on both coils constant. So I will keep the number of turns on both coils constant, because I say the number of turns affects the induced EMF according to the theory that you have studied. So then to collect and analyze data, I will take the following steps. So I will number my steps for easy reference. Step number 1, I will build the experimental setup. Let me first draw the diagram of the experimental setup. Of course, you have the diagram in the skeleton, so it becomes even easier to draw it. So for you can use the ruler perfectly to draw a very beautiful diagram, but I'll also try to draw a better one. So I will need a bench. My apparatus will be laid on a bench. I think I should change the color. So let this be the bench where the apparatus is going to be laid. And you need the coils. This is the easiest diagram to sketch, I think. So I must have two coils. I'll get a guiding point for the coils. Because the second coil I'm going to put it on an iron core, that one is easy. I'll just draw a line for, I will just draw an iron core here. So I want to fix this, so let me just attach this to something that I can easily fix on the table. So I'm now drawing the coils. Okay, so I'm going to fix my coil onto the table. Then for this one is easy because there is a guiding tool here. Okay, so you can draw a better diagram with a better number of coils. Me, I just want something for reference here. So I will fix this coil using a G-clamp. I have attached something here through the coil, which can be used to fix it. It could be a small wooden piece of material, or it can be, you can use a ruler to fix the coil. So I fixed it with a G-clamp onto the table. Then I can also fix this one too with a G-clamp. Okay, so that is a G-clamp. So I have to connect, I must have a cathode ray oscilloscope this side, so I will put a CRO this side. So this is a calibrated CRO. So, but I said you could put an SC, you could use an SC meter. So you could use an SC meter instead of a calibrated CRO. Then this is an ion core. So this is going to be coil Q, and this is going to be coil P. So coil P, on the other side of coil P, I have an ammeter. I have a resistor. Because I may want to find a PD across this resistor, so I'll put a voltmeter across. Then I may want to find R from V over I, so I need an ammeter which is in series. Then on this side I can also put a CRO connected to the power supply. So I'll put a CRO this side connected to a power supply. So this is a calibrated CRO. So this one will help me to find the frequency of the EMF, which is, of course, this is connected to an alternating power supply, so it is going to give me the EMF of the EMF, the frequency of the EMF of coil P. Okay, so these are G clamps. I think I've named everything that I need to name. The rest of, if I've used the rest, if I have used a standard symbol, I don't need to name them because it is a standard symbol. Maybe this is the table. And of course, I must ensure that the distance between these two is constant. That's why I've tried to fix them onto the table. So that is going to be my diagram. So it means now writing becomes very easy. So I will build the experimental setup. Let me change to blue. So I will build the experimental setup as shown above. I'll build the experimental setup as shown above. So step number 2, of course, I have to clamp. I've shown that I would clamp the coils, but I may want just to explain why I have clamped them, but it's not very necessary. The examiner will know that you have clamped because you want them to be at the same distance. So I will clamp the coils on the table so that the distance between them, or between the coils, remains constant. So I have clamped the coils because I want the distance between them to remain constant. Okay. Step number 3. I have to tell the examiner that I will use a large number of turns on coil Q so that E is large enough. So I will use a large number of turns on coil Q so that E is large enough. So that E is large enough. And number 4, so to determine R, If I want to determine the resistance R, then I will determine the current. I will determine the current, I, and the PD across R. And the PD across R, which I'm going to call, which is V. The PD across R, which is V. So R is going to be V divided by I. Alternatively, I'm saying instead of determining this, I'll put this in another column. I will measure R using an ohm meter. Measure R using an ohm meter. Ohm meter. So instead of using V and I to find R, you would just read it directly from an ohm meter. So this is another way of doing it, but me, I've chosen to measure I and V, then use find R from V over I. Then step number 5, I will determine F. I will determine F. Remember, that is the frequency of the EMF in coil P. I will determine F from the oscilloscope. And of course, we know that you have to tell the examiner how you will determine F. We know that F is equal to 1 divided by the period. F is 1 divided by the period, and the period, how do you determine the period from the cathode ray oscilloscope? This is going to be the time base multiplied by the horizontal distance. So period is the horizontal distance times the time base, and yet amplitude or EMF is the vertical distance times the Y gain. So this is times horizontal distance. That is how you get the period. That's how you did it in waves of paper 2. Alternatively, if I don't want to do that, I told you that I would also use a signal generator, so I will put this in brackets. Another alternative, I would have used a signal generator in the place of a CRO on the left hand side, a signal generator. I would have used a signal generator in place of the CRO. For a signal generator, F is read directly from it, where F is read directly. That F is read just directly, so that is another way of doing it. Of course, you don't write both at the same time in an exam. I'm just giving you an alternative because me, I'm a teacher. Then step number 6, I will now determine, of course, you have to determine the EMF the other side. So I will determine E. I will determine E from the CRO. So there's another CRO on the right hand side. So I will determine E from the CRO. But how do I determine E? E is going to be the Y gain of the CRO times the vertical distance. Times the vertical distance. And I have also mentioned in my skeleton when I was planning this to think about how to do it. I also said you could use an SC voltmeter in the place of the CRO. So I'll write it here. I would have used an SC voltmeter. You can't use a normal voltmeter to measure alternating current, alternating voltage, which is induced in coil Q. So it must be alternating an AC voltmeter. in place of the CRO, where for the AC voltmeter, here E is read directly, where E is read directly. So there E is read directly. Okay, then step number 7. So you have now to change R. You choose a different value of R. So I will change R. I will change R and determine, of course, I will determine the corresponding values of E. So in other words, you are going to repeat some steps here. You change R. Of course, you have to determine the corresponding value of I. Remember, you have to adjust to make sure that V is constant. So I will change R and determine E, or determine the corresponding value of E until I have 6 sets of values. Until I have 6 sets of values. The number 8. So after having 6 sets of values, the next thing is to plot a graph. So I will plot a graph. We have already seen on the first page which graph we shall plot. So I'll plot a graph of 1 over E against R. And of course, this is going to be a straight line. So a straight line, but remember this straight line does not pass through the origin. So a straight line which does not pass through the origin. A straight line which does not pass through the origin shows that the relationship is valid. So a straight line which does not pass through the origin shows that the relationship is valid. Okay, then number 10. Of course, we had to find M and K. So to find M, we have already seen that M is going to be 1 over 2 pi FV times the gradient. So you have to tell the examiner this, what M would be, and we have also seen what K would be. So you tell the examiner that K would be 2 pi F V times Vm multiplied by the y-intercept. We have seen this on the first page. Then for safety, of course, now safety precautions. So I would say that for safety, what will I do? I will use, because I expect that the wires would become hot, you must use a heat-proof gloves to touch the hot coils, or to avoid electric shocks from high voltages. You'll use insulating gloves, or you could switch off the power supply before touching the circuit. So I would say for safety, I will use heat-proof gloves to touch the hot coil P and the hot resistor. Of course, the resistor may warm up, so and yet you have to change it. So I'll use heat-proof gloves to touch the hot coil P and the hot resistor R. Or I could wait until they cool down, or wait until the circuit cools down. Then for electric shocks, to avoid electric shocks or to avoid shocks, from high voltage, I will use insulating gloves. I will use insulating gloves or switch off supply, or I will switch off power supply before touching the circuit. Before touching the circuit. I think that is my essay. I think I've tried to write everything. I just need to read it through before I go to another question. This experiment, R is the independent variable and is the dependent variable. I will keep V constant by adjusting the CRO. I will keep the number of turns on both coils constant. To collect and analyze data, I will take the following steps. I will build, so step number 1 is I will build the experimental setup as shown above. I will clamp the coils on the table so that the distance between the coils remains constant. That is very important. I will use a large number of turns on coil Q so that E is large enough so that it is measured with a smaller percentage uncertainty. To determine R, I will determine current I and PD across R, that is V. Then R is V over I. And I said alternatively, you could use an ohm meter to measure R directly. I will determine F from the oscilloscope. Remember, F is 1 over the period, and the period from the oscilloscope is time base times the horizontal distance of one cycle. Then I would have used a signal generator in place of a CRO where F is read directly, but here I used the CRO. I will determine E from the CRO, and E is Y gain times the vertical distance. I've showed that. Instead of the CRO, I would have used an SC voltmeter, which gives E directly by just reading the peak. I will change R and determine the corresponding values of E until I have 6 sets of values. I will plot a graph of 1 over E against R. A straight line which does not pass through the origin shows that the relationship is sorry, it's good to read through. Shows that the relationship is valid. So in step 10, M will be 1 over 2 pi f V times the gradient, and K will be 2 pi f Vm times the y-intercept. For safety, I will use heat-proof gloves to touch the hot coil P and the hot resistor R, or wait until the circuit cools down. To avoid shocks from high voltage, I will use insulating gloves or switch off supply before touching the circuit. So I've written exhaustively. Question number 2. A student investigates how the volume of a gas varies with its temperature. Air is trapped in the transparent cylinder of diameter d with a movable piston as shown in the figure. The distance between the base of the cylinder and the bottom of the piston is h. Okay. The trapped air heated by placing the cylinder in water of temperature theta. The increase in temperature of the trapped air causes the piston to move. When the piston stops, the value of h is measured. From each value of h, the volume V of the trapped air is calculated. The experiment is repeated for different values of theta. It is suggested that V and theta are related by this expression, where K is the Boltzmann's constant, P is the atmospheric pressure, and Y and Z are constants. A graph is plotted of V on the y-axis against theta on the x-axis. So I must make sure that v is the subject. So PV is equal to y k into theta plus z. So I must break theta from z. So I have that PV is equal to y k theta plus y kz. So I will divide by p because I need v to be alone. So v is going to be y times k divided by p, but this is multiplied by theta plus y k z over p. So if you try to compare this equation with y equals to mx plus c. On the y-axis you have v, on the x-axis you have theta. So it means the gradient is going to be y k. So the gradient is y k over p. The gradient is y k over p, and the y-intercept is y k z divided by p. That is the y-intercept. Values of theta and h are given in the table. They have given us theta and h. The volume V, so the value of D is constant, 27.9 plus or minus 0.1. The volume is calculated using the relationship V is equal to pi d squared h over 4. Okay, so this is going to be equal to pi, then times the units. Let me check the units. V is in meters. V is in meters cubed, so it means I have to change this. So this is going to be pi times 27.9 times 10 to the power of minus 3, but this should be squared, divide by 4. Then h was in millimeters, so I'll say times h, which should always be changed to meters. So this will be times the value of h, which is multiplied by 10 to the power of minus 3 to change it to meters. Okay. Then for the uncertainty, of course, the uncertainty in V, we have d squared and h, the multiplication and the power. So it means the fraction uncertainty in V divided by V is going to be twice fraction in D plus fraction in H. So that means absolute in V is going to be into brackets 2 fraction in D plus fraction in H, then times V, times the corresponding value. Let's try to fill the table here. So for the first one, we are finding V. V is going to be pi times 27.9. I want to put this in brackets. 27.9 exponent minus 3, but this should always be squared. Then times the value for h, which is 62.4 exponent minus 3. Then this is divided by 4. So the power minus 5 has already been catered for. So this is going to be 3.8. Of course, these are three significant figures, and D was also three significant figures, so I will maintain just three significant figures. So this will be 3.81 times 10 to the power of minus 5. Okay. So then the next one is going to be pi. I'll just keep repeating this. Pi times 27.9 exponent minus 3 squared, then times 65.2 exponent minus 3 divided by 4. So this is 3.99. Then the third one is pi times 27.9 exponent minus 3 squared times 68.1 exponent minus 3 divided by 4. So this is 4.16. The next one is pi times 27.9 exponent minus 3 squared, then times 70.9 exponent minus 3 divided by 4. So this is 4.33. The next one is pi into 27.9 exponent minus 3, but this is squared, times 73.3 exponent minus 3 divided by 4. So this is 4.48. And then the last one is pi times 27.9 exponent minus 3. This is squared, then times 76.1 exponent minus 3 divided by 4. So that is 4.65. Okay, so next is to add the uncertainties plus or minus. So for the uncertainties, I don't need the power of 10. I don't even need to convert. Remember, it is twice absolute fraction in D plus fraction in H, then times the value of V there. So I'll just use the values here. So it is twice fractional in D. The absolute uncertainty in D was 0.1. It is 0.1, so I don't need to waste time. And D is 27.9. Okay, so I'll say 2 times 0.1 divided by 27.9 plus, for H it is just 0.1 divided by 62.4. So this is times the value of V, which is 3.81. Of course, the power of 5 will remain there, so I don't even need to waste time on it. So this is 0.03. The next one is 2 times. Of course, the first one will be the same, so I'll just say the first one is the same, 2 times, so it is 0.2 divided by 27.9. That will always be the same, plus for H will change, 0.1 divided by 65.2. Then times the value of V, which is 3.99. So that is 0.003. 0.03 to one significant figure. The next one is 0.2 divided by 27.9. Remember, it was 0.1, but there is a 2 times. So that is plus 0.1 divided by 68.1. Then times the value of V, which is 4.16. So it is 0.04 to one significant figure. The next one is 0.2 divided by 27.9 plus 0.1 divided by 70.9, then times the value of V, which is 4.33. So this is still 0.04. The next one is 0.2 divided by 27.9 plus 0.1 divided by 0.1 divided by 73.3 times the value of V, which is 4.48. So that is 0.04. And the last one is 0.2 divided by 27.9 plus 0.1 divided by 76.1 times the value of V, which is 4.65. So this is 0.04. Okay, those are the uncertainties in V. So next is to plot a graph of V against theta. Remember, V is times 10 to the power of minus 5. So you must be very careful with that. Okay. So I'm now going to plot the graph. I'll have to write the values down so that I don't always go back to the table. So V against theta. Okay, so I've written the values down. So the first value theta is 23. The scale on the x-axis is 30 minus 20. The scale on the x-axis, 30 minus 20 is 10 divided by 10. So the scale on the x-axis is 1 degree Celsius, one box. Then the scale on the y-axis is 3.8 minus 3.7, that is 0.1 divided by 10, that is 0.01. So the scale on the y-axis is 0.01. Type, of course, times 10 to the power of minus 5. Okay, so 23 against 3.81. 21, 22, 23 against 3.81. So 3.81 is one box. So this is the point. So I'll draw a small circle around it to make it visible. Then the next point is 35 against 3.99. 35 against 3.99. I think 3.99 is here. Then the next point is 48. 48 against 4.16. 48 against 4.16. 1, 2, 3, 4, 5, 6. 1, 6 is here. The next point is 62. 62 against 4.33. So 62 against 4.33. So 4.3, 1, 2, 3, 4.33 is here. Then the next point is 73. 73 against 4.48. So 73 against 4.1, 2, 3, 4, 5, 6, 7, 8. So this is 4.48. And the last point is 88. 88 against 4.65. 88 against 4.65. So 88 is here. 1, 2, 3, 4, 5. 4.65 is here. So that will be the point. So I have to put this on the same scale, the same page, so that I can now plot the graph, the line of best fit. So I'm now plotting the line of best fit. It is hard to plot the line of best fit on my computer, but I'm trying my level best. That's not a good line because you have to balance the points. Normally check and see if you have plotted them carefully so that, especially if when you see that the line of best fit is not coming out very well, check again. 3.99, 4, 1, 2, 3, 4, 5. This was 4.16, okay? 4.33, 1, 2, 3. Then 4.48, okay? The last one is 4.1, 2, 3, 4, 5, okay? So I'll have to fit them on the same page for proper judgment. Okay, you can't watch this on your phone. I think you have to use a computer to watch this. So I'm trying to bring the point at the bottom closer, but it's very hard. So most likely I'm going to create an anomaly because I can't leave 2 points on one side of the line. So I have to create an anomalous point here. So I'll just draw this line of best fit. You can try to make a better judgment than mine. Okay, so I've created an anomalous point which is at the bottom because I couldn't really bring it closer to the line of best fit unless I plotted wrongly. 1, 2, 3. I think this point was plotted wrongly. 1, 2, 3. It is supposed to be here. I plotted 24 instead of 23. So 1, 1, 2, 3. So it is here. But still, even if I redraw it, it will still be slightly far from the line. So I will maintain that line of best fit. You can draw a better line than mine. I'll maintain that because of time. Okay, so next, so I have to plot the error bars. The error bars are easy. So I can label this line of best fit, line of best fit, or best fit line. Then I'll draw the error bars. Remember the scale on the vertical is 0.01 for one small square. The first error bar was 0.03. So I'll add 3 at the bottom, 3 at the top. So 1, 2, 3. then 1, 2, 3 on the top. So next I just do a vertical bar. The second one was also 0.3, so I'll count 1, 2, 3 at the bottom. You use a perfect ruler to draw a perfect neat horizontal line. 1, 2, 3 at the top. Then I'll draw the vertical error bar. No, that has shifted a little. Okay. Then the next one is 0.04. So I'll count 4 up and 4 down. 1, 2, 3, 4. It is up to here. 1, 2, 3, 4. So I'll draw the vertical line through it. You can pass the pencil there twice so that you make it extremely visible. Then the third one is 0.0. The fourth one is 0.04. So I'll count 1, 2, 3, 4. Then 1, 2, 3, 4 up. So I'll join these error bars. Then the next one is also 0.04. So I'll count 1, 2, 3, 4. 1, 2, 3, 4. Then I'll draw the vertical error bar through it. And lastly, remember this was the point, so I have 1, 2, 3, 4. And 1, 2, 3, 4. So now I will just join this. Remember to draw a better line of base fit because me I'm drawing on a computer, which is really very hard. So I'm done with the error bars. 1, 2, 3, 4. Okay, I'm done with the error bars. Next is to draw the line of worst fit. To draw the line of worst fit, I should have this on the same page, so I have to reduce this size because I must have all the error bars in focus. Make proper judgment. I'll change the color. Let me use green for the line of worst fit. So the method is very simple. You can begin by trying the top of the top error bar and the bottom of the bottom error bar and see if all error bars are crossed. If there's one error bar which is not crossed, then adjust your line so that it is also crossed. So I see that the second last error bar at the bottom would not be crossed. So I have to bring it into focus so that all error bars are crossed. So I adjust the line to the second bottom error bar. So my line will look like this. I have to adjust this. I want it to exactly pass through the second bottom. Okay, so that is going to be my line of worst fit. So I will just simply label it line or worst fit line or simply worst fit. The examiner will understand worst fit. The examiner will understand that. Then the next thing is I will draw now a triangle. I will draw a triangle to find the gradients because I may need the gradient of the line of the gradient and the uncertainty, so I must find the gradient of the worst fit and the gradient of the best fit to be able to find the uncertainty in the gradient. So I'm looking for points where the grid lines cross at the center. If I fail to find such corresponding points, then I'll be forced to draw two triangles. But I will take this point and this point here so that I draw one triangle at the top. Okay, so I've drawn one triangle here, crossing this point and this point. Then at the bottom, I'm also looking for 2 points where the grid lines cross the center. Where the straight lines cross the center of the grid lines. For example, I have this point here and this point here. So I'll draw a triangle at the bottom here. The horizontal line of the triangle will be here. So that's my triangle. The triangle should be visible. You can pass there the pencil twice so that the examiner can easily see the triangle you have used. Okay, so I will have to write out the values. So this point here I have on the blue line. For blue, I have the x value is 23, I think, and the y value is 33.85. 1, 2, 3, 4, 5. Then for green, I have this point here. The x value is 28. Is it 28? No, it is 27. Because the examiner will verify if you read the values correctly. So this is 27. Against the y value is, of course, 38.5. 3.85. 3.85 because the y value is the same. So then up here, for the line below, the x value is 80, 81, 2, 3. That is 83, and the y value for blue is 4.60. Then for the green line, the x value is 83, and the y value is 1, 2. So that is 4.62. So I will just write these values so that I use them to find a gradient without wasting time. X2 8383, Y2 4.62 and 4.60. X1 23 for blue, 20. I'll just write them down so that it is easy for me. For the best fit, X1 is 23 and Y1 is 3.85. For the worst fit, X1 is 27 and Y1 is 3.85. Then for the best fit, X2 is 83 and Y2 is 4.60. For the worst fit, X2 is 83 and Y2 is 4.62. Okay, so let's go here, find the gradient, determine the gradient of the line of best fit, include the absolute uncertainty. So I'll just find the gradient of the best fit. This will be y2, which is 4.60 minus y1, which is 3.85, divided by x2, which is 83, minus x1, which is 23. Then the gradient of the worst fit is going to be y2, which is 4.62, minus y1, which is 3.85, divided by x2, which is 83, minus x1, which is 27. Okay, so let's find these values very fast. 4.6 minus 3.85 divided by 83 minus 23. So this is 0.0125. Okay. Then the other one is 4.62 minus 3.85 divided by 83 minus 27. So this is 0.0138, the same number of significant figures. So then the uncertainty is going to be the difference. So you just take 0.0138 minus 0.0125. So this gives us 0.0138 minus 0.0125, which is 0.00, how many decimal places? I think that is 13. Okay, so it means the gradient here is going to be 0.0125 plus or minus 0. I may want to write 4 decimal places. There is no problem with that. So that is 0.0013. Okay. The next, determine the y-intercept equal the absolute uncertainty in y. So we have to find the y-intercept for the best fit and the y-intercept for the worst fit, and then we subtract to find the uncertainty. So from the equation of a straight line, y is equal to mx plus c. So it means the y-intercept is going to be y minus mx. So I'll say c for the best fit. I'll take the one y value from the best fit and its corresponding x value. I'll take the values at the bottom here, 23 and 3.85. So the y value is 3.85. Oh yeah, I've forgotten something, the power of 10. V was times 10 to the power of 10. Did I consider it here? The y values have times 10 to the power of minus 5. So I'll just add here times 10 to the power of minus 5 times 10 to the power of minus 5 times 10 to the power of minus 5, because here there is times 10 to the power of minus 5 times 10 to the power of minus 5. Okay, so I could write this as 1.25 plus or minus 0.13 times 10 to the power of, I've moved it through 2 steps, so that is power minus 7. That would be the gradient anyway. Okay, so I had forgotten the power of 10. That is very important. So y is going to be times 10 to the power of minus 5, then minus the gradient. The gradient is the best fit gradient, which is 1.25. Or I can just take 0.0125 times 10 to the power of minus 5. So this is going to be minus 0.0125 times 10 to the power of minus 5, then times the x value, which is 20. I've taken this point here, so it is 23. So times 23. Then I'll find C for the worst fit, which will be, I'll take the worst fit value. I'll take the same point which is here, 27 and 3.85. So the y value is 3.85 times 10 to the power of minus 5 minus the worst fit gradient was 0.0138 times 10 to the power of minus 5, then times the x value, which is 27. So I'll press my calculator. So I have 3.85 exponent minus 5, then minus 23 times 0.0125 exponent minus 5. So this is 3.56 times 10 to the power of minus 5. Then the second one is, if I see that they're exactly the same, I will have to increase the number of significant figures because an error of 0 is not acceptable. 3.85 exponent minus 5, then minus 0.0138. I have to start with 27. 27 times 0.0138 exponent minus 5. So to 3 significant figures, this is 3.48. 3.48 times 10 to the power of minus 5. Since they are the different numbers, different values, so I can find the uncertainty. The uncertainty here is going to be the difference. That would be 3.56 minus 3.48. Of course, times 10 to the power of minus 5. So I'll say 3.56 minus 3.48, which is 0.08. 0.08 times 10 to the power of minus 5. Or you could write 8 times 10 to the power of minus 7. Okay. Using your answers to A, C Roman 3, C Roman 4, determine the values of Y and Z, include appropriate units. Okay. So I want you to remember that the gradient from the first page, the gradient was equal to Y times K divided by P. So if I want to find a value for Y, so Y will be P times the gradient, and I will divide this by K. So this will be P, which is 1.01 times 10 to the power of 5 pascals times the gradient. Remember, the gradient of the base fit was 0.0125 times 10 to the power of minus 5 divided by K. K is 1.38 times 10 to the power of minus 23. So I'll press my calculator here. 1.01 exponent 5, then times 0.0125 exponent minus 5, divide by 1.38 exponent minus 23. So I'm getting Y as 9.15. 9.15. Why do I say 5 and write 8? 9.15 times 10 to the power of 20. Okay. Then Z, of course, we saw that Z was related to the y-intercept. So we can simply say that Z is equal to P times the y-intercept. Just look at the first page of this question, then divide by y times k. This is what we found. So P is 1.01 times 10 to the power of 5 times the y-intercept. We take the best value, which is this one here, 3.56. 3.56 times 10 to the power of minus 5 divided by y value, which is 9.15 times 10 to the power of 20 times the k value, which is 1.38 times 10 to the power of minus 23. Okay, I'll check with my calculator. 1.01 exponent 5 times 3.56 exponent minus 5. Divide by, I'll divide by each of these, or I can open two brackets. Divide by 9.15 exponent 20, and again by 1.38 exponent minus 23. Then close the outer bracket. So this is giving me 284, or approximately 285. Okay. Then units, because they said include appropriate units. So y, I can check the units for y. This is pascals, and this is, the gradient was meter cubed Okay, let me start with Z. I think Z is y-intercept, that is in per meters cubed. Is it meters cubed? Y-intercept is meters cubed, and P is pascals. Pascals is newtons divided by meters squared, then times meters cubed, divided by Y, then K is joules per Kelvin. K is joules per Kelvin. But we had temperature in degrees and the change in degrees. So it means, of course, this one reduces this, it becomes Newton meters. Newton meters the same as joules, so this joules cancels out. So we remain with 1 over per Kelvin, which is Kelvin, or it will be degrees Celsius because the temperature was in degrees Celsius. So Z is going to be in degrees Celsius. Or it can be Kelvin, but I think it will be degrees Celsius because we had the x-axis was degrees Celsius. However, this was per Kelvin, that is for every change in Kelvin. And a change on the Kelvin scale is the same as a change on the degrees Celsius scale. That's why I'm saying the answer is going to be degrees Celsius. Then this one, let's check this for Y. P is newtons over meters squared. The gradient we have meters on the y-axis, so that is meters cubed on the y-axis divided by degrees Celsius on the x-axis. Then K is joules divided by joules per Kelvin. Joules per Kelvin. Remember, a change in Kelvin on the Kelvin scale is the same as change in the degree Celsius. So this can be joules per degree Celsius. So degrees Celsius cancels out. This one reduces this to newtons meters divided by joules, but Newton meter is the same as the joule, so it means this one has no units. No units. This was joules per Kelvin, which is the same as joules per degree Celsius. So it means degrees Celsius cancels out. Newton per meter squared is pascals times meters cubed over degrees Celsius, which was the gradient. Then this newtons per meter squared times meters cubed becomes Newton meters. And Newton meter is the same as the joule because Newton meter is force times distance and work done is force times distance, work done is in joules. So this one has no units. Then determine the percentage uncertainty in Y. So I just need to look for something which has Y, such as the one having maybe the gradient, or I could also use the y-intercept. But for the y-intercept, K was not. Anyway, I'll just use for the gradient. So using this expression here, I'll use that expression. I think K has no uncertainty, so I'll not consider it in the uncertainty. So the fraction uncertainty in Y is given by that. When I multiply it by 100, it becomes percentage uncertainty. Should be equal to the fraction in P plus the fraction in the gradient. Then I will multiply this by 100 to make it percentage. So this will be for P. P is 0.01 divided by 1.01. I don't need the power of 10 because it will cancel out. Plus, for the gradient, it was, the uncertainty in the gradient was 0.0013. 0.0013. So 0.0013 divided by the gradient was 0.0125. I will not add the power of minus 10 because it will cancel out. Then this is times 100. So this will be percentage. So 0.01 divided by 1.01. Then plus 0.0013 divided by 0.0125 times 100. So I'm getting this as 0.10%. 0.10. So the answer here is 0.10%. Then the experiment is repeated. Determine the temperature theta that gives a value of H of 60 millimeters. So I have to find V here. V is equal to pi d squared H divided by 4. This will be pi. D is constant, 27.9 times 10 to the power of minus 3, but it was squared. Then times H, which is 60, times 10 to the power of minus 3. We divide this by 4. So this is pi times 27.9 exponent minus 3. This is squared times 60 exponent minus 3. Divide this by 4. So this is 3.668 times 10 to the power of minus 5. That is V. But I want to find theta. So from the first equation, I'll make theta the subject. So theta is going to be, let's see, what is the first equation? So I'm making theta the subject here. So I have PV divided by YK equals theta plus Z. So theta is going to be PV over YK minus Z. Okay. So theta is going to be PV divided by Y times K, then minus Z. So when I substitute P, I have the value of P above here. P is 1.0, 1 times 10 to the power of 5, then times V, which is 3.6668, times the 10 to the power of minus 5, divided by Y. The Y value is 9.15 times 10 to the power of 20, then times K, which is 1.38. K is 1.38 times 10 to the power of minus 23. 1.38 times 10 to the power of minus 23. Okay, so I will press the calculator. 1.01 exponent 5 multiplied by 3.668 exponent minus 5 divided by, open two brackets, 9.15 exponent 20 times another bracket, 1.38 exponent minus 23. Close the second bracket. So I'm getting theta as 293. 293 degrees Celsius. So the answer is 293 degrees Celsius. Okay, so that marks the end of this. I could have made some errors. I may not be extremely accurate, but at least I give you a picture of how to answer these questions. In case of any challenge, you can always write to me. I can always try my level best to answer the questions. In case of any errors, you are free to criticize. I don't care. I just want to give a picture. I'm just recording these videos for my future students so that I reduce the work I do. So there's no big deal here. Okay. Until next time, bye bye.